gives me. Got it. Yeah, it gives me great pleasure to have Oana Matei here today. I first met her at the University of Bucharest when I was a postdoc there, and she just kind of you were already working, I think, in Arad at the time, and you just kind of would arrive like this super cool, badass person who would just kind of throw down on like all sorts of like issues to do with kind of early modern science, and I was always really kind of in awe and impressed by your work even back then. So I mean, she's just a complete powerhouse. Like actually many of the Romanian women who I met working on early modern science were all kind of these really badass powerhouses, but you were definitely among them. Oana's work focuses kind of broadly on early modern plant science, so botany. She kind of does a whole range of really interesting things in relation to this, looking at kind of the use of Baconian natural histories and how it is that kind of, and plant science kind of lends itself especially well to this kind of thing. So it was a lot about kind of collections and looking at specimens, but also kind of looking at plant science in relation to kind of natural philosophy. So theorizing about the kind of underlying or fundamental causes of things like generation and vegetation and things like that. And she also has written stuff about the role of using plants to kind of construct remedies, pharmaceuticals and therapeutics and things like this, and kind of the importance of enacting these kinds of recipes to kind of develop, maintain a kind of knowledge network and things like that. She sort of primarily focuses on early modern, like the natural philosophy in early modern England, but I've definitely seen her throw down on continental philosophers as well, people like Matei and Descartes. And so on. I just really love Oana's work. I think it pushes back against some things that have been kind of these traditional narratives in philosophy. So philosophers of science tend to understand science through sort of the development of things like celestial mechanics and kind of what we think of as physics in the early modern period. But the work that Oana does really pushes back against this, showing the importance of plant science and sort of understanding plants as living things and how this kind of, allowed us to unearth a lot of kind of fundamental processes and causes in reality and things like that. It also, brings to the fore the work of people that we traditionally have sidelined and ignored in early modern science. So, and so we sort of no longer have to focus on just, the canonical seven. We can look at the work of other figures who were very important at the time, and one will mention many of them today, I think, but people who we don't have name recognition of them today, they've been ignored. And I think also your work tends to bring to the fore how important women's work was to early modern science as well, through the role of kind of things like recipes and growing plants and things like that. So lots of things to be excited about with Oana's work.
Well, I'm overwhelmed. Thank you so much. I really am impressed by you made me look like a rock star or something. I'm not far from that. Actually, I accidentally ended up working on the role of plants and their natural processes in the 17th century. When I first started working on the 17th century, I just told earlier to Kirsten about this. I went to London, to the British Library, and I wanted to find Transylvanians. Transylvania is part of Romania, so I wanted to find Transylvanians that in the 17th century traveled to London and were somehow involved in experimental scientific activities. And I was able to discover one. His name is János Banfi. He was he was connected to the Russian College, which preceded the formation of the Royal Society. He had classes of chemistry there. But while I was working on the manuscripts and the archives, I was struck by the fact that all over the place there were discussions about plants. And when I say plants, I'm referring to vegetal bodies in general, whether they are trees or herbs, so plants in general. Everybody was speaking about plants, about agricultural projects, and about fertility, fertilizers, how to fertilize the land and how to make England the most, productive in terms of agricultural production in the world. And it was why was this topic so important? And that's how I started to work on experiments with plants and experimental projects with plants in the 70s. So far, I mostly focused on the methodology of experimentation and how experiments with plants and their methodology contributed to the rise of modern science. What I will speak about today is something that myself and my colleague in Bucharest, Ana Jaladanu, together we work very closely, something that we said that it can be a case of a lost science of life. A science that has to do with plants, but it was not exclusively interested in plants. A science that studies the fundamental processes that take place all over the universe. You have to imagine that in the 17th century, people used to think that the universe is somehow made of the same kind of matter. The same kind of matter that you find in stars, you have in plants, minerals, animals, and the human body. Also the same kind of processes. So bearing that in mind, the idea is that this lost science of life is interested in natural processes taking place all over the bodies in the universe, but the focus on plants is not just for practical reasons, but one part of the story behind is practical. Why? Once, because everybody, or well, all the characters that I speak today in the 17th century, they had a garden or access to a garden, and they could have, specimens taken from the garden and put it into different experimental setups. Two, it was also cheap to do that. So it was not just, but also practical and cheap. And also it's easier to study, to try to study some processes in the case of plants as, or compared to animals. So it's easier to try to study something by the means of a plant instead of by the means of an animal. So why is it a lost science of life? Because if we regard it through Kuhnian, for instance, lenses, then it is, and it would be classified by Kuhn as, non-paradigmatic, rather qualitative than quantitative, although I will present some quantitative aspects that are involved in these experimental trials. And I think, again, if we look it through these lenses, then it is something that didn't win the scientific revolution. This perspective went very well in the second part of the 17th century, and it up to the, let's say, mid-18th century, it started to be regarded through different, using a different key of interpretation. However, for less than a century, it was something that interested a number of naturalists. So, if you allow me, I will start my presentation. So plants as instruments of knowledge in the early modern philosophy. Something else. Again, just as general remarks. What is specific for this lost science of life is that somehow it opposed Aristotelianism and Aristotelian scholasticism, but in many cases, it encompasses some of its perspectives, and I will speak about the substantial form and how Aristotle thinks that generation is taking place. So one thing would be to reject the Aristotelian theory of generation, and the second would be that it was based on using plants as using plants as laboratories where you as a naturalist can study how the natural processes are used. So I will investigate the aggregation of a lost science of pre-modern world, a body of knowledge based on recipes. Some of these, I don't know, I will call them experiments. However, also the notion of experimentation, experiments, experience in the 17th century has a long discussion behind. So they are experiments in the sense that in most of the cases, you have the human intervention, but not in all the cases you have the entire description with, I don't know, ingredients used, how they vary, the parameters, or I don't know, the recording. I mean, the recording of the experiment is not something that we, I don't know, could trace back as being experiment. So I will call them experiments, but bear in mind that for the 17th century, I think we can rather look them as recipes that travel from one author to another via, I don't know, works, correspondence, so on, so on and so forth. So it was built on recipes, observation, and experiments that aim to answer very general questions regarding the origin, nature, and generation of life. This early modern science of life was called sometimes philosophical chemistry, other times vegetable philosophy, science of vegetation. And again, it does not have a place in today's classification of sciences. It is not agriculture because although it's interested in fertilizers and improvement, it encompassed a transmutational perspective, transmutational in the alchemical science, right? Transmutation from something that it has a kind of nature, watery, as the alchemist would put it, into something that has a different nature, oil, or I don't know, mercury, sulfurious. Although it is interested in the manipulation, its objects and the production of meraviglia, it is not natural magic because it aimed to explain and elucidate some of the most general natural processes and transformation. Natural magic was not very much interested into methodology. It was rather focused on results. It's not natural philosophy because it had a definite practical and operative outlook directed towards manipulation and improvement. The disciplinary unity of this body of knowledge was grounded on a common vision. Its practitioners saw plants as chemical or alchemical laboratories. Now a note on the terminology. As Bill Newman and Lawrence Principe proved, the use of chemistry, alchemy, chemical before the 18th century was interchanging. So people referred to the same thing and used different names such as chemistry or alchemy. And also their pioneering work in this sense, perhaps you are very well familiar with it, somehow re-established alchemy in a different, in its own place as the precursor of chemistry. So it's not natural magic because, it's not natural philosophy because it's operative and oriented towards manipulation and influence. Gardening, plant cultivation, and experiments that involve vegetables, trees, herbs do not seem at the very first glance to be philosophical, right? However, in England, in the second part of the 17th century, many natural philosophers, among which there is a list here: Francis Bacon, Thomas Brown, John Evelyn, John Beale, Nathaniel Woodward, Henry Power, Nehemiah Group, perhaps also of the names are not familiar to you. They were actively involved in such activities and were not interested just in the utility of these experiments. Their concern went even beyond the study of external and internal features of plants. So they were not botanists in the, let's say, late medieval Renaissance sense of what a botanist would do. The only apparent common feature shared by the characters of this talk is an interest in plants. Some of our authors are keen gardeners, others are naturalists who want to understand the nature of vegetation. Some see plants as potential medicines or a basis of a healthy diet. Others attempt to exploit the hidden entities of plants as ingredients of natural magic. Some want to improve the land, others are interested in much more theoretical questions, such as whether plants are alive and sensitive creatures. And of course, there are those for whom plants are merely complex aggregates of mechanical corpuscles, automata of a sort or another. In other words, what looks like a common interest in plants and vegetation hides a wide variety of philosophical opinions and practical and even less practical concerns. And yet, in the 17th century, many naturalists were engaged in similar experimental exploits. They experimented with germination and fertilizers. They attempted to make plants grow faster, produce bigger fruits, sweeter fruits. They placed seeds under the microscope. This was a very important step in the study of plants. So they placed seeds under the microscope or into the vacuum pump. They distilled plants, they reduced them to ashes and tried to revive them. Experiments of the palingenesis of plants. Despite their very different interests and perspectives, these people often did the same experiments. As I've mentioned, recipes circulated around, among them. And they attempted the same trials. They often communicated results and exchanged information. So how could this all happen when their perspectives were so divergent? In the past decade, we saw a growing interest for the early modern experiments and experimentation, and also for the role, the part that plants played in this bigger picture. But unfortunately, most of these studies try to see plants, or they only saw plants as a part of the wider picture. They were interested in natural magic and they saw that plants had a role in, I don't know, the recipes that were part of natural magic. The same with, so again, plants were just part of a larger story. There are, of course, several exceptions, pioneering studies of Charles Webster, Antonio Clericuzio, Oana, and Marie Ross, and more recent investigation into the nature of vegetation by Baldassari and Blanc. Works by Baldassari, Clericuzio, Jaleveanu, Mondoina, Cristina Rusu testify the fact that the wider community of early modern scholars has discovered that there is a lot to be said about early modern philosophers interested in plants and agricultural projects, alchemists interested in the principles of vegetation, chemical philosophy in the botanical gardens of Europe. In the past years, scholars attempted to answer this question by appeal to practices, traditions, common sources, and methodologies. One answer, for example, was that all these characters were sharing a kind of loosely Baconian methodology experimentation. They read and attempted to further elaborate on Bacon's natural and experimental history. And this is the cover of Bacon Silva Silvarum, a work which is made of 1,000 experiments divided into 10 chapters. We have many eclectic experiments there, from experiments with the production of sounds, musical instruments, plants. They feature very well in Bacon Silva Silvarum, that occupy 3 centuries there. And also in the last century, for instance, in century 10, you have experiments with, the mind, trying to, the point would be to study how action at a distance is produced and to try to influence with the mind, some reactions to other people that are in the other corner of the room. So again, a very eclectic work, strange, super strange to the contemporary eye. And as I told you, 3 centuries, 300 experiments in Silva's environment dedicated to plants. So many of them circulated around, starting with the mid-17th century, the second part of the century after Bacon's death. This is undoubtedly so. So they have in common this Baconian methodology of experimentation and the desire to combine natural and experimental histories. But it does not fully explain the disciplinary unity of the enterprise I discussed today. Another answer identifies behind all these diverse ways of looking at plants a common interest in the process of vegetation. So we study plants because actually we want to study the process of vegetation. Again, this answer is correct, but far too restrictive. I claim that what gave unity to this early modern experimental investigation was the common vision of plants as alchemical laboratories, as instruments of transmutation. Naturalists that I will discuss today are only interested in plants because they provide access to this universal, latent, and irreversible process of nature. Philosophers had different names for this process. Some, as Bacon, called it concoction, others fermentation. There were naturalists that didn't want to define they didn't want to define their beliefs in theoretical terms, such as I will show Robert Shell. I will show that they shared the same common vision. As I'm going to show in what follows, 17th century naturalists and natural philosophers took these recipes and beliefs, most of them, from vacancy environment, as a starting point for a thorough laboratory investigation. They integrated plants in their laboratories, but they also aimed to enter into the laboratory of plants. Microscopes were used to open up plants and dissect seeds. And some at least hoped to use these newly developed instruments to observe the actual motions of generation and growth taking place in their samples. As we shall see in what follows, the characters of my talk were keen experimenters who tried to devise quantitative measurements in order to figure out the economy of a plant's chemical transmutation. How much water was turned into salt. They tried, to compute the quantities of water. There is this very famous, but we will discuss it later, the very famous Van Helmontian experiment, the willow tree experiment. They use experiments to clarify questions and sometimes even to amend their theories and change their philosophical allegiances. This is something that bears the Baconian, we've had this discussion earlier, that according to Peter Ensley, Alberto Banzo, and I fully agree with them, this is something that bears the Baconian mark of natural and experimental history. You, as an experimenter, would start with some theoretical assumptions, right? You do experiments, and the point would be to illustrate your theoretical assumptions. What happens if the experimental results do not prove your theoretical assumptions? What do you do then? If you are an Aristotelian, you would say that, okay, something happened, the experiment went wrong because, I don't know, the conditions in the room were as it were. But if you are a Baconian, you would try to adapt your theoretical considerations to your experimental results. I'm not saying that they dropped out their hypotheses. I'm just all their theories. I'm just saying that they were willing to adapt them according to experimental results. So as Peter puts it, Peter Ensley puts it, the experiment prevailed. In other words, behind what was usually taken to be a common but loosely defined interest in plants, our characters display a form of disciplinary unity. They are pursuing a close investigation of the chemical transformation that takes place in the laboratory of the vegetable world. The aim was to observe, understand, imitate, manipulate, and transform these chemical transmutations. They also aim to use this knowledge in other fields, medicine, for example. This scientia is not botany. It's not science of plants, properly speaking. Is more an experimentally based, bottom-up construction of a philosophical investigation for which plants are useful instruments of knowledge. In most general terms, the key object of their investigation, the universal and irreversible process they pursued, was described in two ways. The first way was to say that plants turn water or watery juices that they used to draw from the earth into something that has a different nature named oil, right? In the alchemical language, the mercurial is transmuted into sulfurics. So this was one way to see the transformation of water in oily, and again, the idea was even to compute it possible, the quantities. The second way to describe the universal irreversible process of vegetation was to say that it turns tangible gross matter, such as water, mixed with various substances, fertilizers like niter, for instance, into spiritual, active, living matter, right? So again, a short discussion about what spirits are in the 17th century. So we are not talking about angels, God, not that spirits, right? Ghosts. Spirits are subtle entities. They, most of the times, they are corporeal. But the difference is that their corpuscles or particles of matter, the matter they are made of, is of a subtle nature. The second point about spirits, you have a universal spirit of the world diffused all over the universe and is active in matter. So these spirits, they enter matter and they, through their activity in matter, they perform different transformations of this matter. The idea is that spirits are imprisoned in all the bodies in the world, like in a stone or in a plant or in a bottle of cider or in a glass of wine. And they have the natural tendency to escape the imprisoning body in this world and to reunite with their connatural. And they are, again, in trying to escape, they are very active. And in this activity, they create even more matter, matter of the grosser kind. Okay, so these are spirits. So the point would be to investigate this process as the transformation of tangible matter into spiritual, under the action of these spirits that, again, they are spiritual matter, they create gross matter, but they create even more spirits because they want to reunite with their connatural and escape their, I don't know, imprisoned body. Plants perform a pneumatization of matter, and during these transformations, plants were able to turn spirit into new forms of life. Think of an old tree in the forest. Its bark is covered with moss, mushroom, ivy, mistletoe grows on its branches, little insects are crawling up and down. Its trunk, the characters of this stalk, would see this old tree as the perfect laboratory for the investigation of the production of all these spontaneously generated forms of life. They would see moss, mushroom, and ivy as superplants. Growing from an eruption of sap to the bark, they would take insects to be byproducts of the same sap, forms of life arising from the tree itself. Right? So think of games, for instance. They were very interesting specimens in the 17th century. The naturalists of the 17th century were super puzzled about the idea that you would have insects growing out of a tree. How is this possible? To illustrate these claims, I will first discuss some instances for the investigation of the transmutation of water into oil in the laboratory of plants. Then I will discuss how the process through which nature creates living bodies is explained by some naturalists of the mid-17th century. Okay. And I will take the case of two microscopists, Henry Power, we will get to that, and Nehemiah Go. What's important also is I would like to show you how the microscope helped Power and Grew to work with conflictual hypotheses. Transforming water into oil. Much of what is going on in a plant is hidden to senses and hence quite difficult to ascertain. what the experimenter has to do is to find good examples and illustrative experimental setups, which would allow us to see, visualize the phenomenon, and which would also allow to control and measure the input and the output of a given experiment. As Francis Bacon puts it, in all generation and transformation of bodies, it should be asked what is lost and what is given off, what stays behind and what enters. In the Silva Silvarum, Bacon proposes a group of experimental investigations which aim to do just that. Plants were taken out of their natural environment and cultivated in such a way that the experimenter can regulate the input of water and water nutrients which enter the experiment. In some of these, plants are set into water, so without any kind of soil. In others, in humid environments, onions were hung in the air, put in, I don't know, a cloth filled with water. Cloth soaked in water. In some cases, plants and seeds are set at a certain distance from a pot of water. There is this very nice experiment with the cucumber and the cucumber seeds that are placed on a plate at some distance of, I don't know, some water, and to see if the water is sucked by the cucumber and if the cucumber grows in by soaking that, drinking the water. To see if the plant can attract water. The same kinds of experiments are performed with different kinds of water, varying the parameters in a controlled manner, and extended to include not only water in solutions, but sap. What is sap, according to the 17th century natural philosophy, is a juice that was already concocted by the plant. So the plant extracts the juices from the earth, but what we have in sap are the juices of the earth already concocted. So they are already prepared by the plant. Experiments of inoculation, for instance, grafting buds or placing seeds inside the bark or the roots of other plants to see if the resulting plant feeds upon the sap of the host. All these experiments investigate the same thing, the conversion of water, what Bacon calls concoction, the gradual and unbroken process through which water and watery substances are transformed into oil and oily substances. In the 6040s and 6050s, we can find these experiments taken over. Oh, I'm sorry. This is a very nice example of damask rose with the root upright in an earthen pan full of fair water without any mixture. Okay, so this is an example of experiments with plants to see how to transmute water. So I will move. What do they show? Water, okay, are the main nutrients of plants. This was a key question in the 17th century. Which is the principle of life? And Van Helmont was keen to prove that water was the principle of life. And the willow tree experiment was intended to prove exactly this. The willow tree experiment, so Van Helmont claimed that he took a willow tree branch. No, I'm sorry. He took the willow tree branch and he took some earth that first was put in the oven, and he tried to dry it as much as possible. He weighted the earth after the soil. That was taken off the oven. And then he placed this branch of willow tree, and he claims that for 5 years he added water to the willow tree branch that developed. So he measured the quantity of water that was added, and after that, after 5 years, he looked comparatively to what he started with as the willow tree branch and what turned out to be after 5 years. And also he took the soil from the pot, he put it into the oven, he dried it, and he noticed that it was very the same amount of earth that he started with 5 years ago. 5 years before, I'm sorry. So he claimed that actually this drew him to the conclusion that the earth didn't do anything. It was the same quantity, so the willow tree didn't use any kind of earth. What did the work was the water, which was added permanently, and he knew what quantity of water he added in 5 years. So this again drew him, this made him to draw the conclusion that water was the principle of life. Water did everything for the willow tree to develop. Okay. So in the 6040s, 6050s, we can see first that this mid-17th century naturalists began with a list of plants very similar with what we can find in the Silva silvarum. Please take a look at this. This is Ralph Austin. He writes a book which is called Observations upon some part of Sir Francis Bacon Natural History. Actually, it's the subtitle of Silva silvarum. What Austin does here is to take most of the experiments with plants from Bacon's Silva silvarum and to retest them and to mark observations on each experiment and to add some theoretical explanations whenever he felt it. Thomas Brown, for example, began with Bacon's list of plants, which included mint, majoram, bark, pennyroyal, as well as bulbous roots, plus seeds of all sorts of plants. Bulbous roots and mints were important because the mint, and of course bulbous roots also, they feed a lot on water. So that's why they were major for these experiments. Brown attempted to diversify the list and to identify which plant can survive in water long, for instance, years in a row. He also tried different kinds of water and water solutions to see whether this variation will lead to a modification of the properties of plants. He also included among his experiments vials with water in which no plants were set in order to see the process in which the water under the influence of heat and light undergoes by itself a process of concoction and spontaneous generation. In the period of 6059, such experiments figure proeminently in the experimental investigation, correspondence, and publication of John Beale, Robert Sherrock, Robert Boyle, and Ralph Austin. We can find in their works attempt to extend the list of plants that undergo the experiments mentioned before, and even to use the property of plant to convert water as a basis of natural historical classifications. A new kind of classification which is based not on visible features, on the visible features of plants, but on their property to grow in water itself. Robert Sherrock. Okay. So Robert Sherrock, in the History of Propagation, classifies plants according to their hydroponic properties. He divides his samples into plants which, one, if set in water, did not grow at all, but died before developing roots. Two, are able to develop leaves and sometimes even roots, but which nevertheless altered and died before attaining maturity. And three, seem to develop normally in vials of water. He assumes that plants transmute water and looks into the further investigation of it. For example, one question Sherrock asked was how much such plants could increase in weight and how much water was thus converted. Okay, and please take a look at this part. I'm sorry. The results were carefully recorded. And he says, sedum multifidum in amounts increased in weight havus crupples, cordium as much in a fortnight, donas, his Woodward grew in 6 weeks, 30 grams. Bugula in somewhat less time grew 15. Watercress grew 25 in a month. Ranunculus had a scrapple in 6 weeks, and periwinkle as much. Prunella, brookline, scordium, and most of the sorts of nymph that weigh proportional. Like Bacon, Brown, and Sherrock, John Beale and Boyle also supposed that plants can transmute water, and they discussed experiments intended to investigate the qualitative and quantitative details of this chemical transformation. Boyle recollects the main lines of these investigations in the Skeptical Chemist, published in 1661, and later in The Origin of Forms and Qualities, published in 1666. We can see that Boyle uses the same basic list of plants whose properties were established by Brown and Sherrock, and he attempts to extend it with various variations of his. Like Bacon and Brown before him, Boyle seems to be particularly interested in what parts of water fit the plant, whether the effect is to be attributed to pure water, to a universal principle or spirit dissolved in water, or whether plants absorb salts and other chemical substances that water merely dissolves. Experiments discussed in the Skeptical Chemist and later in Origin of Forms are said to demonstrate two things. First, they disprove the hypothesis that plants extract from water, and I quote, saline and other elemental substances of the earth, end of quote. Second, they display the transmutation, providing the naturalist with, and I quote again, pleasure of seeing the progress of nature in the transmutation of water. And end of quote, says Boyle in The Origin of Forms and Qualities. What happens in the plant is a real transmutation, a phenomenon which can be investigated not merely by seeing the plant growing or by weighing the input and the output, but also by distilling the resulting plants and by showing that they contain a considerable amount of oil. And I quote, yet perhaps that it is not less strange, which we elsewhere relate, that a plant consisting chiefly of transmuted water did by distillation afford us a true oil that would not mingle with water and consequently was easily convertible into fire. And I quote again, this is from The Origin of Forms and Qualities, and the second quote is also from the same book. So from that inoculations, we may learn that a phlegmatic liquor that seems homogeneous enough, but very slenderly provided with other manifest qualities than common water, may, by being variously contexted by buds of trees, be transmuted into bodies endowed with new and various and considerable signs, colors, taste, solidity, medicinal virtues, and diverse other qualities manifest and apart. A hot topic in the early Royal Society was represented by the investigations into the properties of sap. Again, we can find a number of recordings of the Geological Committee, which was established in the 1660s. And also we have some articles published by John Beale in the Philosophical Transactions. I think it was in the 1668 and 1669. The Causes of Mineral Springs is the first one, and Dr. Beale's Instances, the second one. And they read almost like a summary of the whole discussion we did before. In those papers, I'm not going to read this. That's in those papers. We can find a whole series of questions raised by such experiments, from the capacity of plants to transmute water to the various phases and stages of transmutation, which can be investigated with the help of these natural alembics. Hence, we may suspect that the very contextures of their bodies of trees from the first spurting of their seed, and as they are formed gradually from the invisible principles of spirit and vigor of the seeds, however small and imperceptible, are the natural limbics or alembics, where the common rain, water, and air are digested into very much different leaves, fruits, seeds, raisins, and nuts. Okay. So let's move now to the microscopical perspective, right? So the microscopical perspective, I will put it differently. The first naturalists that worked on plants were very much interested to see what is happening in the sea. Now you have these two, let's say at least two traditions that were in a kind of tension in the mid-17th century. One comes from the Aristotelian way of explaining the process of generation as an actualization of something that is in potential, right? So matter would be actualized by form, the substantial form. And for instance, in the case of a chicken, you would see how the embryo would develop gradually. And this theory is called epigenesis, right? So the embryo is formed, parts of the embryo are formed gradually, but perhaps you know more about epigenesis than I do. The other theory was the preformist theory, who claimed that all the characters of the plant were pre-existing, pre-formed in the seed. And the process of growth was nothing more than the enlargement of the seed. So the idea would be to have, and Harvey did a number of experiments, not with plants, but with eggs, to study the development of the chicken embryo, and he concluded that, again, he was an epigenist, so he concluded that the embryo would develop in different stages. But not everybody was, supporting his point of view. And I will discuss about Henry Power, who is, by the current secondary literature, considered to be a preformist, particularly because he was obsessed with seeds. However, I claim that he was not, I don't know, the preformist theory was not the only theory on his working paper. So the use of the microscope allowed naturalists to delve into a universe of formerly not visible entities. Along with this possibility, some naturalists saw the opportunity or the promise to visualize even the last division of matter, atoms. Power was hoping that the microscope would allow him to see atoms. Of course, it was impossible to see atoms, even Power realized that. But he hoped that at some point, the microscope will evolve as much as to allow him to see atoms. We discussed about the preformist theory, so I will say that actually he uses, in spite of what current secondary literature claims that he was the preformist, I will say that he used the microscope to deal with conflictual hypotheses that were on his table, to decide whether all the features of the future plant are embodied in the seed or not, or some processes of transformations are taking place in the seed instead of, just enlarging something that already pre-exists. And also, I think that he uses, while he tries to use the microscope in order to, again, to visualize atoms, but also to deal with Cartesian corpuscularianism and the other theory, as a development, right? The other tradition that claims the action of spirits, right? So Cartesian corpuscularianism would say that a plant is nothing else than an aggregation of particles, an automata. The principle of individuation, I think, is given by, I'm not a Cartesian scholar, so I hope I'm not saying something that is not accurate. I think the principle of individuation is given by the disposition of particles and immutatio, right? I think immutatio is the process through which a living body arranges its particles according to the complexity that that body has. For instance, something that is non-living, according to Descartes, such as stones, would have, I don't know, the motion of the particles would be in a circular direction, while something that is rather more complex, such as the human body or an animal body, would have the particles moving in a spherical direction. So that's the, this imitatio arranges the particles and makes them move, a certain way. So what I'm saying is that our use the microscope to, to not to distinguish, but to see at play, in the case of plants, how these two conflicting hypotheses are illustrated. Who was Power? He was a member of the Royal Society, but an atypical one. He didn't live in Oxford. He was a physician, first of all. He practiced medicine. So he was a remote member of the Royal Society. He did not attend to their meetings. So again, an atypical member. He published just one book, which is called The Experimental Philosophy. If we go to words that are important for my claim that we have an experimental kind of science, real modern science, then I would say that this guy here is someone that really emphasized the role of experiment in the title of his book. So he published just one book. It was published in 1664, but apart from that, he left a large number of manuscripts. Most of them are held in British Library in the Searle collection. And I think that what we have in the experimental philosophy is just the tip of the iceberg. A number of work is to be found in the manuscripts and in his correspondence. So a reading, the experimental philosophy is divided into three parts. The first one is called the microscopical experiments. I think the second one is, the second one is mercurial, and the third one is magnetical. So we have three parts. Experiments with plants are part of the first one, the microscopical experiments. Well, actually, they are called experiments because this is how Power speaks about them. However, they are not experiments in a proper sense. They are rather observations of plants. So observation 38 to observation 45 in the experimental philosophy are those dedicated to plants. They reveal Power's interest in the microscopical studies of seeds. Out of the 8 observations on plants included there, 4 are dedicated to seeds of diverse plants, moonwort, walrus, strawberries, and pumpkin. In 2 other observations, namely observation 42 and 44, Power mentions and makes comparisons with seeds. Therefore, although Power dedicates only 8 out of the 51 observations included in the microscopical part of his experimental philosophy of plants, 6 of them would examine seeds. So, according to the preference interpretation, right, this, let's say, profound interest into studying the seeds of plants would be proof that he was somehow working into this direction. Consequently, his interest in providing that plants formerly considered to be seedless, in fact do have seeds. Let's take now a look at observation 39. It has been the opinion of all herborists that the capillary plants had no seeds, which error did rise merely from a popular inadvertency. For though these plants carry not their seeds in visible husks, pods, spikes, fruits, and the like, yet they are constantly to be found on the backside of their leaves. So this was something that he discovered actually that ferns do have seeds on their leaves. I suggest that the preference position was not the only theory, right? It's true that the microscope offered him the possibility to observe small entities. And he notes that the seed of strawberries look, and I quote, look not unlike the strawberry, some reddish, yellowish, and green colors, as the strawberries themselves are, and I end the quote. But the similarity between the appearance of a plant and its own seed is not a sufficient proof, and I don't know, the similarity of colors is not a sufficient proof for Power's preference position. Moreover, in his published, he owned in his own library a copy of the experimental philosophy, so a copy of his own. And there is a note made in his handwriting, this comment. And in this comment, he says, seeds are seeds are as it were nature's cabinets. Yes, here it is. So what is a cabinet of nature? What if cabinets of nature are places where, I don't know, diverse transformations are taking place? So again, if we discuss the preference interpretation, then I'm not sure that it's the only theory at play here.
Excuse me, you only 5 minutes.
Oh my God, I only have 5 minutes. Okay. Oh, I haven't realized that. Okay, a different reading would may hint that, again, this cabinet of nature is rather an open, a closed place where, like in a laboratory, nature performs diverse transformations. Okay, then I will skip through the next discussion of how, we can discuss it over the Q&R session, how he tries to distinguish between the corpuscularian, the Cartesian corpuscularian theories and other, let's say, more universally generative theories. And I will skip through, it's interesting, and I would like to discuss this with you. There is this is an experiment of how a plant can produce an insect. And he says that every plant can produce their particular insects, right, out of, again, their nutritive properties and by the action of spiritual movement. Okay, so let's move to again, he worked with the microscope. He was a physician too. So also please note that apart from, let's say, theories in natural philosophy, many of these characters were physicians, and they were working with the medical theories in the 17th century. He extensively published on plants. He was employed by the Royal Society. I think he was the first, right? Their first employee.
No, Hooke was the first, but
Hooke was the first. Okay.
Groo's employed roughly the same time.
Exactly. Okay, thank you. So he was employed, he was a curator, and the Royal Society supported his investigations into the realm of vegetal bodies by facilitating him access to a microscope. It was not cheap to have a microscope back in the 17th century. I think it's not cheap today, so even worse in the 17th century. I will move to, because what I'm trying to discuss with you today is just, of course, a small part of Bruce's perspective on plants. I will try to discuss with you the role of artificial generation of bodies for our understanding natural processes of plants. So Gru claims that everything in nature is made of atoms. Atoms more or less the Democritian kind of atoms, well, let's say that Gru had his own idiosyncratic way of understanding what an atom is. So everything in nature is made of atoms. These atoms are the last indivisible, immutable units of nature, and they mix. The natural processes are mixtures. Mixtures in terms of bounding atoms together. Okay, and here we have, I should take this systematically, otherwise it won't be understandable. So everything in nature is made of atoms and structures of atoms. However, it sounds rather difficult at this point. However, in order to have generation and natural processes, atoms and mixtures are not enough. And Gru introduces something that comes rather from the alchemical tradition and is called vegetable principles, out of which he says the saline principle is the preeminent. So you have atoms that are defined as having size, figure, and unit motion. Motion is given by these vegetable principles, which are active principles. If atoms are ontological principles, vegetable principles are active principles, and they have a key role in triggering natural processes such as generation. Gru worked at 3 levels, I say. One is the macro level of bodies, of tree or rows, yeah? You understand what I'm trying to say? The other one was the microscopical level, where he could have access to salts. Here we have he has this 4 division of salts into marine salts, nitrous, alkaline, and acid salts. And here you have them drawn, and here is how they stick to each other, they bound to each other in structures. These are the margins of the leaves of plants. As you see, we have geometrical structures here, and this is the level of crystals of salts that can be observed by the microscope. And the third level is that of the submicroscopical, the submicroscopical level of atoms that cannot be seen with the microscope. But what you can do is to infer the knowledge you get at the microscopical level and the properties that you can grasp at the microscopical level to atoms at the level of submicroscopical observations. This is why he used artificial created bodies, again, to get knowledge that can be used for natural processes that are not observable even with the aid of the increased vision. And it's interesting because we have, these are the plates that are appended to the Anatomy of Plants published in 1682. And it's very interesting that in that Anatomy of Plants, we have, it's called the Anatomy of Plants with an idea of a philosophical history of plants. You have the 2 works, this one and this one, put into the 1682 edition, plus several other lectures read before the Royal Society. And there are 2 lectures. One is called the Discourse Concerning Mixtures, which is a very theoretical lecture, actually is all speculative, only speculations there, where he claims about the atoms, what I told you about the principles of nature. And then you have some lectures which are mainly made of experiments, and this is not my reconstruction, this is something that Gru acknowledges, the role of the other lectures, experiments in consort, which is very common if you want. Kirsty, related to our discussion earlier, So you have experiments which are meant to prove the theoretical claims made in the discourse on mixture. So again, he uses, there is this discourse on, I'm sorry. Well, it's not here. It's a discourse on the essential salt of plants. And this is something, if I can have 5 minutes extra, I'm sure that everyone will be interested to find out about the palingenesis of plants, which is the resurrection of a plant out of its ashes. So this idea goes back to Paracelsus, who claims that if you burn a wood out of its ashes, or in those ashes, you can spot the 3 hypostatical principles important in the Paracelsian argument. The flag, mercury, the oil, sulfurous, sulfur, and the ashes would be the principle of salt. Paracelsus claimed that if you put those ashes obtained after you burn the tree into earth out of, I don't know, in a certain amount of time, you would have the same tree growing. These experiments were taken over by other Paracelsian figures, such as Joseph Duchenne. He experimented with nettles. So he reduced nettles to ashes, put them in a fan, somehow in open air, and after a while you would see the, I don't know, some crystals form there, and Duchenne would say that the crystals that we see there, they represent the essential salt of the plant. What's the role of this essential salt? The role is to bear the substantial form. So you have in the essential salt, if you look at the ashes of the nettles, you would see crystals that resemble the nettles. What does this prove? This proves that actually you have the essential form there. Okay, so this is Duchenne's addition to experiments with the palingenesis of plants. There are nice recordings of Kenneth Rigby, for instance, who tried to do experiments with the palingenesis of plants. And he said that it was impossible to have successful results because plants are imperfect bodies. However, he claimed that he was successful in experimenting with the palingenesis of crayfish. It's very funny. He claims that he reduced the crayfish to ashes and then he added for a number of days, what would you expect other than ox blood? So he put it ox blood there and he waited and he waited and he put it more ox blood there, and at some point, some little, I don't know, entities started to move around the pot, and if you add more ox blood, you can have them grow as more as you like. So this is the palingenesis, but the point would be to prove that there is an essential salt of plants that varies the substantial form. So Gru would use the same kind of experiments to prove that there is no substantial form, but the form is contained in the angularity, regularity, and the geometrical disposition of the crystals. And the same kind of properties you can infer by translation to, well, this is my reconstruction, of course, to the level of atoms. So that's it. Thank you very much.